Hello and welcome. This presentation is brought to you by Science Visualized. Today we are looking at Organic Chemistry 1, where we are looking at the reactions of alkyl halides. And alkyl is generally abbreviated as R, and then the halogen or halide is X, where the halide can be fluorine, chlorine, bromine, or iodine. So the halogens, group 7A elements, alkyl halides. Example of alkyl groups could be a methyl group, so CH3 methyl fluoride, or methyl chloride, methyl bromide, or methyl iodide, or you could have even longer chain alkyl groups, like in this case, an alkyl iodide. Alkyl halides participate in two types of reactions. The first one is called substitution, and the second type is called elimination. In substitution reaction, you start with an alkyl halide and then react that with a nucleophile, and you end up now with the halide portion substituted by the nucleophile, and then the halide becomes the leaving group. For the elimination reaction, number 2, you start with an alkyl halide and then react that with a base instead of a nucleophile, and what ends up happening is that you end up eliminating that hydrogen, so the base will deprotonate that hydrogen, and then these bond electrons will flow here to become a double bond, and then the leaving group, the halogen, will leave, and you end up with an alkene as the product plus X plus base now connected to that hydrogen. So that's the elimination reaction. Substitution reaction can occur in two ways. The first one is called SN1 reaction, and the second one is SN2 substitution reaction. Similarly, elimination reaction can occur through E1 or E2. Now, some books will just write this as E1 and E2, or E1 and E2. Same thing with SN1 and SN2, SN1 or SN1, but it basically means the same thing. So SN1, the S part stands for substitution, N is for nucleophilic, and 1 is unimolecular. That means the rate of an SN1 reaction depends on the concentration of only one substrate. So uni there means 1. So only on the concentration of the alkyl halide. On the other hand, SN2 again will stand for substitution, nucleophilic, but now the 2 part is bimolecular. That means the rate of the reaction depends on the concentration of both the nucleophile and the substrate. So you depend on the concentration of both the nucleophile and the concentration of the alkyl halide. The alkyl halide is the substrate. Similarly, for E1, E stands for elimination, and then 1 is unimolecular. That means the rate of an E1 reaction depends on only the concentration of the substrate. And again, the substrate in this case is alkyl halide. E2 stands for elimination bimolecular, where now the rate depends on the concentration of the base. Remember, we use the base for elimination. We use nucleophile for substitution. So the base and the substrate. Substrate again is alkyl halide. Now let's go ahead and look at the mechanism. And we will start with SN2 reaction. So for SN2, you start with an alkyl halide. In this case, I will draw an example. An alkyl bromide. But now we want to show the stereochemistry at this carbon. So you have a hydrogen going in and another CH3 coming out. So that's a CH3. And then react that with a nucleophile. And a basic nucleophile in this case. You can either use a neutral nucleophile, which has electron pairs, or a basic nucleophile. The first step, the nucleophile will attack the electrophile, but from the opposite end of the halogen. That's the leaving group. And then the halogen will leave. So the next thing that you will do is to draw a transition state. Because this reaction is concerted, that means all the steps occur at once, as opposed to SN1 and E1, where the reaction goes through a carbocation intermediate. So in this case, you draw the substrate, but now you start breaking the leaving group, that's the halogen. At the same time, you start forming a bond. Remember, the nucleophile is attacking from the back. A bond to the nucleophile. And then these other two groups here, the hydrogen and the CH3, are now forced to be on the same plane. So H and CH3 on the same plane with this alkyl group. And that is the transition state. So see what's happening here. The halogen bond is starting to break, and therefore you use dotted lines. At the same time, the nucleophile is starting to form a bond with that carbon, so you use dotted line. So two things are happening. The halogen is starting to break, and the nucleophile is starting to connect. And the end result is that now you end up with this product. Again, I will start with drawing the alkyl part. But now, because the halogen has left, you end up now with the nucleophile being connected from the opposite end. So you have the nucleophile here, and then you end up flipping the other groups, CH3 and H, plus the leaving group. And that is the product of an SN2 substitution reaction. Generally, SN2 reaction, when you look at the nature of the alkyl halide, it prefers primary alkyl halide. It's much faster than secondary alkyl halide, and never happens on tertiary alkyl halide. And the reason for that is because primary alkyl halide is less hindered compared to tertiary alkyl halide. And it's favored by what's called polar aprotic solvent. That means solvents that are polar but cannot donate hydrogen. So for example, ethers, ROR, and many others. Now let's look at SN1 mechanism. Again, we're going to use the same substrate. And again, we're using a nucleophile, a negatively charged nucleophile. But in SN1 reaction, the nucleophile does not play a role in the rate determining step. So that means the rate of the reaction only depends on the concentration of the substrate, which is the alkyl halide. So what happens is that in the first step, the bromine breaks away to form a carbocation in that position. So first, The bromine breaks away to become Br minus, while the remaining alkyl part forms a carbocation, but now a carbocation is sp2 hybridized, so that means the hydrogen and the CH3 are all on the same plane, and therefore you have a positive charge on that carbon, and that's called a carbocation intermediate. The stability of carbocations follows the following order. Tertiary carbocations are the most stable. So if we look at the carbocation stability, tertiary is more stable than secondary, which is much more stable than primary, which is also more stable than methyl carbocation. And because of that, SN1 mechanism will be fastest in tertiary alkyl halides, followed by secondary alkyl halides, and never happens for primary or methyl alkyl halides. So that's step number 1. You form a carbocation intermediate. Now step 2, this carbocation intermediate now reacts with the nucleophile. So plus the nucleophile. And this nucleophile can attack in 2 ways. Because the carbocation intermediate is planar, that means it's flat, then that means the nucleophile can either attack from the top or from the bottom. So 50% of the nucleophile will attack from the top to give you this product with the nucleophile connected from the top, plus the other 50% will attack from the bottom, so to give you this other product, where now the nucleophile connected from the bottom. And because of that, you end up with what is called racemization. In other words, you get what's almost like what you call a racemic mixture, where you have equal mixtures of enantiomers, because one of the products will maintain the same position where the nucleophile occupies the same position as the leaving group. See where the leaving group is? So this nucleophile is exactly the same position, and we call that retention product, because it retains the same configuration. While the second one has the nucleophile in the opposite position, and that now is called inversion product. So you end up with almost 50-50 mixture of retention and inversion product, and that is called a racemic mixture or racemization. So that means if one of the isomers formed has R stereochemistry at a chiral center, so this chiral center, then the other one will have S. Or if the first one was S, then the second one will be R. So they will be opposite configurations. So SN1 reaction proceeds by racemization. It's much faster in tertiary alkyl halide, and it requires what we call polar protic solvent. This means solvents that can donate protons or hydrogen ions. So for example, water has HOH, so it has an OH alcohols and amines. All of this will be polar protic solvent. Thank you very much for tuning in. Next time we'll look at the mechanism of E1 and E2 reactions. If you enjoyed this presentation, please subscribe to the channel.